Welcome back. This is part 2 of refraction. We're going to talk about lenses and what kind of images we get when we pass light through a lens. So this is going to be very similar to the discussion we had about the mirrors. And where mirrors dealt with reflection, lenses deal with refraction. The light is entering the lens and is coming out the other side. So it's all about refraction. Before we get started, make sure you have that chart out so we can fill in the different type of images we get for the different types of lenses depending on where we place the object. Very similar to what we did, or exactly like we did, with the mirror. So hit pause and grab that if you need to. All right, so just like with mirrors, with lenses, we have a couple of different types. We have convex and concave lenses. If you look at the pictures here, concave lenses, once again, have that caved in look to them. You can define them a little bit more accurately as thinner in the middle. That's a concave lens. And so a convex lens is going to be thicker in the middle. Again, I always had an easier time remembering concave for whatever reason. So again, just thicker in the middle is convex, thinner in the middle. And the reason, or the important thing that comes out of this is look at these exiting rays in the picture. For convex lenses, we're going to have them all coming together and they're going to converge. The rays are going to converge, so it's called a converging mirror, or converging lens. And then for concave lenses, as the rays exit, they never cross, so they diverge. And that's going to significantly affect the type of images that you get from these lenses. Let's start with a concave because we don't really have a lot for it. There's only one case of the type of image we get from a concave lens. And before I tell you what they are, just let me remind you of how similar this is to our mirrors. We have our principal axis here. We have a focal length, but let me point out that there's a focal length on each side of the lens. Remember, our light is entering and exiting, so we have to think about what the lens looks like on each side. And so a lot of the times, just to keep it straight, they use this symbol here. We call it a prime. So we say F prime, we're just talking about the left-hand side or the object side of the lens. Very similar. We're going to place an object in here, and we're going to see how the rays converge or diverge, and then analyze it to see what the image might be. So let's do that for a concave lens. So as I showed you how to do the ray diagram before, we take step 1, go straight across to the surface of the lens, and then we're going to bend it up and away. Up and away. And then the second one's going to go right through the center of the lens. And then what we have to do now is take that first ray that diverged, and we have to trace it backwards. And that's a little bit harder part for these diverging lenses. We have to trace it backwards and see that we have it crossing on the object side of the lens. So here's what you need to write in your chart. The image that we get from a diverging lens is virtual. I know in mirrors, if it was on the same side as the object, it was real, but this isn't a mirror. This is a lens. Your light is actually passing through this lens. So to have an image form on the same side doesn't make any sense. You couldn't project this image. You can't put a piece of paper there and have this image actually show up. So it's just tricks of the eyes when you see it. So it is always upright, it's always smaller, and then on the same side. We could draw a third one here where we go through the focal length, but for this one, for these lenses, two rays is usually quite sufficient. All right, so I got a little bit ahead of myself, I guess. I put the rules a little bit past this, but that's okay. We got the diverging lens out of the way. Always virtual, same side, upright, smaller, all that good stuff. So we have now, we're going to go through the convex lenses. So these are going to be converging, And there's 6 cases. Remember how we had the mirrors and we put the object like within the focal length, at the center of curvature. We're going to do kind of the same thing here and see what kind of images we get. All right, we're going to begin with putting our object very, very far away. As you can see here on the animation, all the light rays incoming are parallel. They're going to be bent toward the normal, and they're all going to come out and pass toward the focal length. And so, since that focal length is actually on the principal axis, there's no change in height. I mean, it's kind of hard to explain this, but it's infinitely small, I suppose you could say. So, in essence, there is no image. So that, if you don't get close enough to a lens, nothing gets through it, or it all gets through it at the same point, depending on how you want to look at it. Either way, there's no image when your object is super, super far away from a converging lens. All right, let's go to the next type. This time we're going to put our object out beyond the center of curvature. That's 2f prime there. That's the center of curvature still. We're going to have our first ray pass through, so let's trace it. The red line here, over and down through the focal length. The second one would pass straight through the center of the lens. And then the third ray here through the focal point, hit the surface of the lens, and then come out parallel. So remember, we have to have 2 parallels, one parallel in, one parallel out, as we do our ray diagrams. These 3 cross here, and that gives us an image. It's upside down. We talked about that before. If it's upside down, it's inverted. This is a converging lens, so this is going to be a real image. Of course you can project it. We pass things through converging lenses all the time. Telescopes, cameras, and things like that. So this is a real image, upside down. Notice the size of the arrow, it is smaller, and it's between the center of curvature and the focal point. So that's case 2 when it's just beyond the center of curvature, the object I mean. All right, let's bring it on in a little closer. Let's put it at the center of curvature, do our ray diagrams, and we can see that here we get an an image that is real. Of course, it's a converging lens, still upside down, but now it's the same size. So this is where you specifically have to be if you're taking pictures to get the image to be the same size as the object you're taking a picture of. Helps to know that information. All right, and next we're going to put the object between the focal point and center of curvature. See how our ray diagrams here come together. The obvious thing that's changed now is the image is very big. So we get our first magnification of the object as the image forms. Still real, still upside down. And look how far the image is beyond the center of curvature. All right, let's keep going. I bet the next one's going to be at the focal point. All right, so there's our first diagram through the focal point. Through, up, here's another blind spot. So just kind of like in our mirrors, when you put an object at the focal length, you're not going to see anything. And then finally, if we get the object really close to a lens, through the focal point, through the center. So this is a case where we can get a virtual image from a converging lens. Don't get too close to the camera. So this is a huge image. It is upright and it's very magnified. So again, that's when you put an object very close to a converging lens. I think you're most familiar with this phenomenon with this thing called a magnifying glass. And that's how we need to put a magnifying glass really close to the object that we're trying to magnify. All right, well, I just have some exercises there. I'm not going to make a video of these, but maybe I'll just go through one kind of quickly just to kind of see what it would look like. So here's that one example that we'll do. An object that is 7 centimeters high is placed 20 centimeters in front of a convex lens, and the focal length is 15. So we're out beyond the focal length. Determine the characteristics of the image. Are we beyond the center of curvature? What do you think? No, the center of curvature is at 30. Remember, that's twice the focal length. So this is going to be an object between the center of curvature and the focal length. Determine the characteristics of this image. In our mirror video, we were introduced to the mirror lens equation, if I do, I die. So we want to use the same equation. Let's ignore the height for just a moment. Let's look at our main variables, the focal length 15, the object is at 20, and we're looking for DI. So plugging it into the if I do, I die equation, we get the image distance to be 60 centimeters. So that's all well and good. So now let's put that information now into a magnification equation, and we do have heights here, so we could use that, or we could use the ratio of distances. Either one, it doesn't really matter. So if I just wanted to use Dido, I would come down here, it would be negative 60 over 20, and I'd get negative 3. In this problem, it's probably a good thing to do this, is we actually went through the effort of finding the heights of the image. So we'll go through that real quick. So if we know image and object distance, that's going to be the same ratio to image and object height. So just rearranging those variables, plugging our numbers for DI, DO, and HO, we can see that image height is negative 21. So that's important. That negative sign there tells you that you're going to have an upside down or inverted image. And then you plug that into the magnification equation with using H's, and you still get that negative 3. So either way, you can figure out that you're going to get an inverted image from that information. All right, so characteristics, type, it is a real image. We have a converging lens. We know it from the math of this because our DI came out to be positive. That means it has passed through the mirror, the lens. So let's go back and let's make sure I didn't do a really good job of pointing this out when I went through the calculations at the beginning of this, because I just assumed something that I should have said out loud. Let's go back and look at our equation here. It's if I do, I die, and it's a plus sign. Now notice when the work started getting done here, suddenly there was a negative sign. Well, actually, I'm going down the wrong path here. So let me erase that and start this over. What I'm trying to say here. This one's actually okay. All right, so what I'm trying to say is this image distance that comes out may not always be positive. When it does come out to be positive, that means your image has passed through the lens. Like we have our lens here. This is where it comes out in a positive direction. You can get a negative direction for this answer. Let's for a moment say you place this thing at 10 centimeters, this object at 10 centimeters. If you can just real quickly work through the mental math for me here, this becomes 1 over 15 minus 1 over 10. Solving for DI in that case actually gives you a negative image distance. So by putting it really close, as we saw in a few slides prior to this, if we put the object really close here in front of the lens, the image is going to reappear on this side. That is a negative distance. So just want to make you aware that you can get a negative number here in this equation. And when you do, that means it's on the left-hand side of the lens. Right is a positive number. All right, well, if you have any questions on that, you really do need to work some practice problems to master that. But the most important thing for a multiple choice test is to understand what kind of image you're going to get from passing light through a lens, all depending on A, is it converging or diverging, and B, where is the object in relation to the center of curvature and the focal length. Let me know if you have any questions.